We're going to take a look at independence versus dependence with regard to random variables. Let's recall that if the probability of event A occurring given B has occurred is the same as the probability that A will occur, in other words, it doesn't matter whether or not B has occurred, it has no bearing on whether or not A is going to occur, then the events A and B are considered to be independent. Well, let's examine this joint probability distribution. We have two categories. We have bought cell phone insurance covering cracked screen. And if we think about this, that's really a yes or no question. Either they bought cell phone insurance that covers a cracked screen or not. And when we think about a probability distribution, our random variable takes on numerical values. But what we can do is let the number 1 be yes, someone bought cell phone insurance covering a cracked screen, and 0 then would represent no. Now, if we were to take, for instance, this cell right here. In this cell, we have two events occurring. One is that someone bought cell phone insurance covering the cracked screen. That's a yes. And they did crack their screen. That's a yes. And so the probability that these two events will occur is 0.35. This cell right here, the way we would interpret this cell is that we have people who bought the insurance covering the cracked screen and they never cracked their screen. And that probability is 0.30. We can articulate what each of these other cells indicates in the same way. Here we have people who didn't buy cell phone insurance covering the cracked screen, and they did crack their screen, and that probability is 0.2. And then the last one is that they didn't buy cell phone insurance covering the cracked screen, and their screen did not crack, and that probability is 0.15. Now let's do this. Let's break out the two random variables here. Let's let X be bought cell phone insurance, or at least bought cracked screen insurance. And again, that random variable can take on the two values 1 and 0, where 1 indicates yes they did and 0 indicates no they didn't. And then let's let Y be the event or the random variable crack the screen. We could then make probability distributions for each of these random variables looking at this joint probability distribution table here. So we have our two variables, X and Y, and then we have their respective probabilities. We have the values of the random variable. So if we were to look at this then, X is here. X bought cell phone insurance covering cracked screen. Y is whether or not they cracked the screen. And the probability that X would equal 1 would be 0.65. Because here we have 0.35 of the people bought cell phone insurance and did crack their screen, and 0.3 bought cell phone insurance and didn't crack their screen, for a total then of 0.65. And then looking at this entry here where X is 0, this associated probability should be 0.35 in order for this sum of the probabilities to be 1. And if we look here, the probability that X would be 0 is 0.35 because the sum in these two cells is 0.35. And now our probability distribution for X is a valid probability distribution. The sum of the probabilities is 1. Let's do the same thing for Y. Y could be 1 or 0. The probability that Y would be 1 would be 0.55. And the probability that Y would be 0 is 0.45. And we get that by adding these cells. And again, we have a valid probability distribution for y. And this column sums to 1, and this row sums to 1, as it should be. Again, let's recall that in order for these random variables to be considered independent, then the probability that y takes on some value given x takes on some value would have to be equal to the probability that y takes on that value. In other words, it doesn't matter what value x takes on, that probability of y would remain consistent. So let's do this. Let's find the probability that y is equal to 1 given x is equal to 1. Looking back, we can see here that y is equal to 1 in this column and x is equal to 1 in this row. So we are given that x is equal to 1, and that probability is 0.65. The probability that y is equal to 1 then would be 0.35 divided by 0.65. We could reduce that to 7/13. Or if we wanted to round this to 3 decimal places using the calculator, we would find 0.538. So we found this probability. Now, in order for us to show that these random variables are independent, we would need to show that this probability, that y is equal to 1, is the same as this conditional probability. If they are independent, then we would be able to show this for each value of x and y. Looking back, the probability that y is equal to 1 is 0.55. So what we found now is that the probability that y is equal to 1 given x is equal to 1 is not equal to the probability that y is equal to 1. If we are going to show independence, we'd have to show that each case works out, that they would be equal. But if we are going to negate independence or show that they are dependent, then we really only need to show one case, which we can see here. These things are not equal. Therefore, the random variables x and y are dependent.